Thanks for the intro, Shivram. Is this on? You can hear me? Yeah, so my name is Shomik. I'm a fifth-year PhD student at Stanford. I'm going to talk about split annotations, which is a system for optimizing data-intensive computations in existing libraries. And this is work that I've done with my advisor, Matej Zaharia. So the motivation for split annotations is that modern data analytics applications combine many disjoint processing libraries and functions. So as an example, in the Python ecosystem, a typical data science pipeline may load some data using pandas, maybe normalize it using NumPy, and then train a model over it using scikit-learn. So on one hand, this is good because you get great results combining thousands of independently written functions in each application. But on the other hand, applications don't benefit from end-to-end optimization across function calls, which prior work has actually shown can leave over an order of magnitude of performance on the table. So why is calling existing optimized APIs slow? One major reason is that on modern hardware, processing speeds have actually significantly outpaced memory access speeds over the last several decades. As a result, data-intensive computations are often bottlenecked by data movement between main memory and the CPU. So as an example of what data movement optimization is and why it's important, here's a typical NumPy program that performs computations over vectors of data. So each operation is highly optimized. It's implemented in C. But because each function executes independently over in-memory values, the overall execution repeatedly scans these values from main memory rather than collectively operating on values that reside in, say, the CPU caches. So this data movement between main memory and the CPU is actually a significant bottleneck on modern parallel hardware, and in fact, it can often be the dominant bottleneck when composing these existing functions. So there are some existing ideas for optimizing end-to-end applications underneath these high-level APIs. And in particular, researchers have proposed JIT compilers and runtimes that can optimize code on a per-application basis. So as a few examples, TensorFlow XLA, TorchScript, Weld, Numba, and Boreum are all recently proposed systems that allow developers to use high-level APIs such as NumPy and Pandas, but perform things like JIT compilation under the hood on end-to-end applications to improve performance. So compilers perform a variety of optimizations, ranging from SIMD vectorization to common sub-expression elimination, but often the most impactful optimizations they apply are in fact the ones that reduce data movement. So compilers can reduce data movement by effectively fusing adjacent operators so they only perform a single scan over the data. And in many applications, this optimization alone has been shown, to contribute most of the speed up over calling individual functions in existing libraries. But the problem with these compilers is that they require a huge developer effort. And in particular, to take advantage of these compilers, you need to replace every function in your library to use the compiler intermediate representation to see the benefits. On top of that, this IR may not even support all optimizations present in already hand-optimized code. So as one anecdotal example, Weld is a JIT compiler from our research group, and it needs thousands of lines of code to support a rudimentary integration with NumPy and Pandas. And because of their complexity, JIT compilers will often also see issues like this. So in this top example, the compiler failed altogether because it didn't recognize a particular operator that appeared in the application. And adding support for it would have been a multi-week effort. And in this bottom example, turning on compilation actually made the performance worse. In this case, the developers stated that some operators are just expected to be slower than hand-optimized ones, since it's too difficult for a compiler to always generate code that matches an expert's implementation. So the question we ask in this work is, can we obtain similar speedups to JIT compilers with only existing functions? So this work, Split Annotations, aims to do just that. Split annotations are a system that provide the data movement optimizations and automatic parallelization while keeping existing high-level APIs, but also without forcing developers to rewrite their library code. So the basic key idea in split annotations is pretty simple. It's that you split data to pipeline and parallelize it. So to see what execution looks like without split annotations, let's look at that NumPy program I showed briefly earlier. When this first function is called, the entire inputs are scanned from main memory to produce a result. When we call subsequent functions, reused values are scanned again entirely from main memory, assuming that the inputs are larger than the CPU caches. And this causes that data movement bottleneck that I mentioned earlier. With essays, we change the way that this execution is actually carried out. The system will build an execution graph, and we can keep data in the CPU caches by only passing cache size splits to each function in the execution graph. So rather than passing the entire inputs to this first function call, we only pass the splits of the inputs that collectively fit in the CPU caches. And then these splits can then be pipelined across all the function calls in this execution graph. We can then process each set of splits in turn, and we can get parallelism by simply parallelizing over the splits. So I want to show you an example of what a split annotation actually looks like, just to get an idea of the effort required to use them compared to, say, a JIT compiler. And to do this, we're going to look at this library called MKL, which is this linear algebra package that's highly optimized and developed by Intel. So here's a very simple function from MKL. It just adds two vectors element-wise. And this is what the split annotation for this function looks like. And just by adding this annotation and adding a small API to go with it, there are some nice benefits that you get compared to JIT compilers. First, you don't need any intrusive library code changes to apply these annotations. Second, you can reuse optimized library function implementations as opposed to having to rely on a compiler to kind of generate code that will match existing code. And finally, you don't even require access to library code to add these annotations. You can just add them from the outside, potentially on black box libraries. And because of these properties, essays can actually sometimes outperform compilers. So in this benchmark, we're implementing the Black-Scholes options pricing model using standard Intel MKL. So with just MKL, remember, it's already optimized, very highly parallelized. This is kind of the performance you get. And the reason that this scaling tapers off at around 4 threads is precisely because of this data movement bottleneck that I mentioned earlier. As you add more threads, the application is increasingly bound on memory access. So after a point, throwing more cores at the problem doesn't really speed up the application. Using a compiler solves this because it performs data movement optimization such as loop fusion. But you can see in this particular application, the single-threaded performance is not as good as MKL because it just doesn't generate code that's as fast as MKL's hand-tuned functions. But with split annotations, you kind of get the best of both worlds. You can still leverage these highly optimized kernels that expert developers have written, and you get the same data movement optimizations that a compiler will provide. So in this particular case, we get a 5x speedup by just reducing data movement over an already optimized library. So there are several challenges in actually designing split annotations for real libraries. The first challenge is just defining how to split the data passed into each function and ensuring that data passed between two annotated functions is safe to pipeline. This means ensuring that operating over split data will produce the same result as operating over entire inputs without pipelining. And this is assuming that the function is actually annotated correctly. The second challenge is building a lazy execution graph of the annotated functions transparently. And since we didn't want developers to modify their libraries, we basically just wanted to demonstrate that lazy evaluation is possible without intrusive code changes to the library. And the final challenge was designing a runtime to execute functions in parallel. So in this talk, I'll mostly touch on this first point, and I'll defer to the paper for a detailed discussion on these second 2 points. So how do split annotations actually enforce safe pipelining? So let's talk about what safe pipelining means first. And we can do this with matrix functions. So if you have a matrix function, we can iterate over a matrix either by row or by column. So if we have two matrix functions that both iterate by row, this is OK to pipeline, because you can split the matrix up by row and pipeline those rows through each of the functions. But if we have one function that iterates by row and another that iterates by column, this isn't necessarily safe to pipeline, because that first function may update that row, and the second function will then read down the column and maybe read some values that it expects to be updated already. So there's a semantic mismatch in the second case where operating on split data is actually different from operating on entire inputs. But that mismatch doesn't occur in the first case. And because we're trying to compose arbitrary functions, the annotation system actually needs to know about these kinds of mismatches. So split annotations use a type system to enforce safe pipelining. The building block of this type system is a new concept called split types, which uniquely define how arguments and return values of a function are split. As an example, here's that VDAdd function I showed from a few slides back. Its annotation assigns a split type to each of its function inputs, and each split type defines uniquely how each argument is split. To define how to split values, split types can actually have runtime values as parameters. So as an example, array split partitions arrays into regularly sized pieces. To uniquely define how to partition arrays into regularly sized pieces, we need both the length of an array, so that's n, and we also need the number of pieces into which the array is split, which the annotation denotes as k. And so k is actually a value that the runtime will set automatically based on the CPU cache sizes, for example. So as an example, array split 1010 uniquely defines an array of length 1000 split into 10 pieces. And this is a different split type from, say, array split 1100. So given the split types in each annotation, we can actually enforce safe pipelining by effectively adding constraints on when a function can operate over split data. So notice that we've assigned the same split type array split to each of the array inputs. This means that our system will only call VDAdd on split data if at runtime the inputs to VDAdd are split in the same way. In addition, we can only pipeline data between two functions if the data passed between the two functions have the same split type. So as a more complete example, let's look at splitting matrices in NumPy, where functions actually let you control whether they occur by row or by column using an axis argument. So we can encode the matrix split type with the Boolean axis as one of the parameters. So if axis is 0, the function is by row, and if axis is 1, it's by column. At runtime, when the function is called, these parameters are initialized with values in the split type. This then lets us distinguish between the two cases that I mentioned earlier. In the left example, the split types match because the two functions assign the same split type to the matrix. This lets rows of the matrix be pipelined between the two functions. And in the right example, the split types don't match because of the axis. If the first function is already operating over split data, we need to merge those split pieces before calling the next function. So how does an annotator actually write essays? It's pretty simple. You first logically define a split type. So this is basically coming up with how values should logically be split and what parameters that depends on to define uniqueness. You then write a split function and a merge function for the type. So this is some code that you submit to the system that physically performs the splitting and merging. And then you use the split types to actually annotate functions using the defined split types. So Mozart is our system implementing split annotations and its runtimes. So the way it works is that developers write annotations and then use a command line tool that will effectively generate a wrapped library which applications will call into. So that wrapped library just has the same API as the existing library with some wrapper code around it. Internally, the wrapped library calls into this client library that's responsible for registering function calls to annotated functions with a lazy task graph. The client library also determines when the task graph should be evaluated. So in C++, we use memory protection to determine when evaluation should happen. And in Python, we use metaprogramming for lazy evaluation. So you can see the paper for more details, but in general, library developers don't need to make any changes at all. It kind of just happens automatically. So after the client library decides to evaluate the graph, the runtime will check split types, split data, and then execute the functions in parallel. Okay, so diving into some results now, there's 3 high-level questions we wanted to ask when evaluating split annotations. The first was what kind of workloads it can accelerate. The second was how much effort it takes to use essays versus compilers. And the third was how essays compared in terms of performance to these JIT compilers. So we demonstrated essays on a variety of libraries. They're all listed here. But perhaps more interesting is the kind of data types and operators that we can support them with. So we supported operations over things like arrays and matrices, but also things like tensors and operators such as joins in a database, grouping aggregations, and even things like image processing algorithms. In terms of integration effort, we found that they require far less effort to integrate compared to compilers, which is perhaps unsurprising. But this pandas integration is specifically telling. So we annotated 15 functions in pandas. Those are the ones we needed for our evaluation. And it took us more than an order of magnitude less code to use split annotations compared to doing that same integration with Weld. So we just had to add these little tags on each function instead of having to do code generation per function and generate IR. In terms of performance, essays can match JIT compilers under existing APIs. So this left result shows simulating the movement of like stars and galaxies in a galaxy using NumPy. And we got a 4.6x speed up over NumPy, but more interestingly, we were competitive with the performance of all these different compilers that are out there, which shows that data movement optimization really is one of the most important ones. And on the right, it's a similar result. We were able to match Weld's performance on this more complex pandas workload that constructs a pivot table and then performs a join and an aggregation. And finally, we can also accelerate these highly optimized libraries, such as Intel MKL and ImageMagick. So I showed the result on the left already, but just to reiterate, just by adding these annotations, we can basically get better memory performance by doing pipelining and getting a 5x speed up over standard MKL there. And on the right, it's kind of the same story. We just added these annotations on these ImageMagick functions, and we got an almost 2x speed up on 16 threads compared to standard ImageMagick. So across all the workloads we benchmarked, we were within 1.2x of all the compilers we tested against in 9 workloads. We outperformed all the compilers in 4 workloads, and compilers actually outperformed essays by more than 1.2x in 2 workloads. So our system was up to 6x slower than compilers in this case. And this generally happens when things like code generation actually matter. So if you have something like interpreted Python doing a bunch of string processing, essays are still going to call that same code, whereas a compiler will actually JIT code for it. So that's where that performance difference comes from. We have a bunch of other analyses in the paper that kind of describe where specific speedups come from, and I encourage you to look at the paper for that. So to conclude, split annotations enable order of magnitude speedups over existing libraries. They require less than 10 times the code to integrate with existing compilers, and all of our code is open source, as are all the experiments and everything, so I encourage you to take a look at that as well. And with that, I'm happy to take questions. Thanks.
Hi, really nice tool. Can I use it now?
You can, yeah. You can install it on pip, and the source code for the C++ implementation is also online.
And another question, a real one. Can you elaborate a little bit about the difference between this and expression templates that are used to construct lazy expression trees and fuse operation and do all that stuff for C++ libraries?
Yeah, so expression templates, you mean things like eigen, for example, in
yes.
C++, right? It's a similar idea. So eigen is more similar to doing, like, I guess, code generation at compile time in some sense, where this is kind of looking at more dynamic libraries where you have specific things that are written and you want to fuse them. So it'll also work with like Java or Python, for example. One other difference is that I think doing parallelism in eigen for certain kinds of operations is a little bit more difficult than doing parallelism here, just because this is a slightly more constrained model.
Thank you.
We have time. Petros Beñares, Google. I was wondering if you think there's any impediment to combining the typical compilations like fusion operations and logical or algebraic optimizations with the split annotations ahead of time, or are they sort of mutually exclusive?
I don't think there's any fundamental challenges with combining them. So the way I imagine this would tie in with compilation is you would basically do compilation in like Python or something using a system like Numba, which will basically JIT code per function. And then you can use something like this to get the kind of data movement style optimizations across functions. But I mean, there's no reason that you could partially do fusion in a compiler and then also use this to kind of do pipelining across things that the compiler doesn't support, for example.
Thank you.
Let's thank the speaker again.